Hello, this is Mrs. Schroeder. We're going to start talking about the third section in Chapter 12. This section covers a lot of different laws, a lot of more unique laws. So we're going to cover these in a couple different parts. Today we're going to talk only about the ideal gas law. So if you're looking at your book in Chapter 12, we're only just doing the very beginning of it. We've already learned some gas laws. We learned about Boyle's law, which said pressure times volume is a constant. Remember, K is a constant. It could be any constant. Every system has its own constant. Charles' law, volume divided by temperature is a constant. Again, it could be any constant. It depends on the system itself. Guy-Lussac's law says pressure divided by temperature is a constant. And Avogadro's law related how volume and number of moles are related to each other through a constant. Now, an ideal gas would always obey these laws. But this is real life. And in real life, no gases are ever ideal under all sets of conditions. Sometimes they behave ideally, sometimes they don't. In this chapter, though, and in this class, we're going to learn about gases that are ideal. We're going to talk about them as if they do, because most of the time they will act more or less like an ideal gas. So an ideal gas does not condense at low temperatures. It's always going to remain a gas no matter what. It does not have forces of attraction or repulsion between particles. So this is a key. We've assumed that gas particles have elastic collisions, meaning they hit something, they bounce off like that bouncy ball against the wall. They never stick to it. They never push off with more force than they came at the wall with. No force of attraction. We also assume that particles have no volume, because the volume of the particle itself is so small compared to the space that it takes up. We've assumed the volume is negligible or insignificant. On the other hand, the real gases actually do have some of these. They actually will condense. If we cool it down enough, a gas will condense. So we have liquid nitrogen. It's a liquid that we've cooled down enough to condense. Sometimes they do attract or repel each other. We've talked about force of repulsion, force of attraction before with the dipole moment. Sometimes they have charges that will attract or repel each other. And particles do actually have volume. It's just very, very small. I'll show you a video on that tomorrow. So the ideal gas law is a way of relating all of these pressure, volume, temperature, and number of moles for an ideal gas. Now, if you get to a high-level class in college, you may learn about how to relate it to a non-ideal gas. But in this class, we're going to relate to ideal gases. You could also mathematically solve and figure this equation out yourself, but in this class I'll just give it to you. So PV equals nRT. Volume times pressure equals N times temperature, and then R is a constant. Now this one is the same constant no matter what, versus the K, which could change depending on the system. This R has a value, and it has units. Now, depending on which units you use, R is either 8.314 or it's 0.0821. You better make sure this is written down in your notes, because you're going to have to know this. The difference between these two, you could actually apply your conversion factors to and prove that 8.314 equals 0.0821 in a different unit. But it's easier to just use the units. If the problem gives you kilopascals, use 8.314. If the problem gives you the pressure in atmospheres, use 0.0821. Now, it is a good model under normal conditions. Most conditions we have, this works for. If we have very high pressures, very small volumes, or particles that have a great attraction to each other, it may not work perfectly. And you could learn correction factors. Again, that would be a higher level college chemistry class. You might learn that in. Now this is just going to show you, again, real gases when they deviate. Most of the time our pressure is, remember atmospheres, 1 atmosphere of pressure is what at sea level. So most of the time we're operating right down in here. Okay? And you can't see that. So most of the time we're going to be down in this area. Okay, close to a normal ideal gas. Something less than 100 atmospheres. That'd be very, very high pressure. So ideal gases, PV divided by nRT equals 1. Anything divided by itself is 1, which is this dashed line across here. That's your ideal gas. So you can tell that hydrogen deviates a little bit. Nitrogen and methane deviate a little bit. They deviate on the other side, and then they kind of go higher than that. But there's a little bit of deviation. The higher pressure you have, the more deviation you have, because as you have higher pressure, you squeeze them together. As you squeeze them together, their space, their volume becomes more important. If their volume becomes more important, they begin to attract or repel each other. Sometimes they do deviate. And again, they deviate the most at high pressures, based on this graph. Alright, we're going to try to solve a problem. Problem number 1 on page 435. So, just like we do with our other problems that we learned for our gas laws, we need to figure out what we're given and put this from a word problem into a math problem. We know that PV equals nRT. That's our equation for our ideal gas law. PV equals nRT. Some people call it PIV-NERT. That's one way to remember it, if you like to have a name for it or a word for it, PIV-NERT. So, question number 1 on page 435. Pause for a second and open your book up to find this. It says, how many moles of air molecules are contained in a 2-liter flask at 98.8 kilopascals and 25 degrees Celsius? So, for our pressure, it said our pressure was 98.8 kilopascals. Now, as it didn't say at a pressure of, it says at 98.8 kilopascals. They expect you to know, based on those units, that that's a pressure. A volume. Unit of volume is liters and milliliters. I have a volume of 2.00 liters. How many moles? They're asking me to find N. My temperature is 25 degrees Celsius. Now, if you remember, all gas laws have to be converted to degrees Kelvin. I add 273 to get 298 K. This will not work if you leave it in degrees Celsius. You'll get the wrong answer, so always switch it to Kelvin for gas laws. Now, I have N, and I want to get N by itself. If I divide both sides by RT, divided by RT, if I look at this, RT cancels out, and I have N all by itself. So N equals P, which is 98.8 kilopascals, times temperature, which is 298 K, divided by R. Which R am I going to use? I look at my kilopascals, and I have to find the R which matches kilopascals right here. So 8.314. So I say make sure you write these down. The units are liters. So notice I have to make sure that my volume is going to be in liters. And I just wrote the wrong thing down up there. PV is supposed to be 2.00 liters. So liters times kPa divided by moles K. So my temperature now is 298 K. So I check my units and see if my units do cancel. And kilopascals and kilopascals cancel. Liters and liters cancel. Kelvin and Kelvin cancels. And I'm left with moles. Moles divided by moles is going to give me moles on top. And when I do all my calculations, 0.0798 moles, and that's my N. Now, I want you to try question 2 on page 435 on your own. Actually, we'll do a little bit of it together, and I'm going to have you try to calculate it on your own. How many moles? Again, they're trying to ask us for moles. Pressure, volume, N equals, NT equals. So how many moles of a gas are contained in a can? with a volume of 555 mils at a pressure of 600 kilopascals and a temperature of 20.0 degrees Celsius. Now I want you to try to solve for n using the same methods we used in question number 1. Double check your units. I have mils there and I have degrees Celsius there. If you notice, R has liters and it has Kelvin. Make your units match, solve for n. So figure this out, show me in your notes that you've got this by tomorrow when I check your notes. And we'll talk about some more of these practice problems in class to see how you do.